Okay, previously we left off, we had just created this merge function and tested it, and we saw that we could merge sorted lists. So if we had a sorted list of 4 elements and another sorted list of 4 elements, the merged sorted list, so this list and this list, would merge. You'd compare the lowest element of each list, and that would drop in to our merged list. Then if this is list A and this is list B, we'd compare 14 and 19. Well, 14 goes in there. Now we compare 27 and 19. Then 19 goes in there. 27 and 35. 27 goes in there. 33 and 35. 33, and then the remaining 3 elements here drop down into our merged list. Okay, so we successfully created this helper function merge. Now we need to work on our actual merge sort algorithm. So all of the algorithms we've used before, we've been keeping track of work, and we return work here. So since this is a recursive function, we're going to have to pass in the work as an argument, right? So we're going to have a parameter up here called work, but anytime we call mySort, we're going to have to pass in whatever work we've done so far, unless it's the first time we call the function. Okay, the first time we call the function, we'll start work at 0. That's what that equals 0 means. So if I don't provide this work argument, then the parameter work here starts out equal to 0. All right, and we can get rid of this now. Okay, so our sorting algorithm starts out, this is merge sort, and what we do is we first have to start with one list of unsorted numbers, and we divide and conquer. We split the list into 2 and then merge sort those lists. So these 2 lists are not sorted, but if we call merge sort, when at the end of that, these 2 lists will be sorted, and then we'll merge them back together. Okay, so we're going to call merge sort on each one of these. But first we need 2 separate lists. So we've created sorted, which is basically our list. It's a copy of the unsorted numbers, so we don't modify unsorted. So we want to make 2 different lists, and we're going to call them A and B. All right, so A is going to be the first half of the elements. So that's going to be, we're going to take a slice. We'll say sorted, and we're going to take a slice. So we're going to start at the beginning of the list. So we leave this first item before the colon blank. That means start of the list. And then where do we end? What slice do we end at? This is going to be the length of sorted divided by 2. Right? So this should give us a slice starting from the beginning of the list to the length of sorted divided by 2. Well, there's a problem if the length of sorted is an odd number. So Python 3, if I have a list 9 divided by 2, that's going to give me 4.5. That's not a valid index. Okay, but if you have been studying up on Python, you know there's an alternate division. This is integer division, and it always gives you an integer result. So 9 divided by 2 is 4. So it's basically division when you divide and try to get a quotient and a remainder. It's the quotient portion. Right? If I want the remainder portion, I can do modulus. Right? So 9 divided by 2, if you want decimal form, is 4.5. If you want quotient remainder form, then you would say the quotient is 9 integer divide 2, and the remainder is 9 modulus 2. Okay, so that means here our slice, it can't be a decimal slice, so that means we're going to have to just use integer division. So B is going to be a slice as well of sorted, but instead of starting at the beginning of the list, we're going to start at basically this spot, this exact thing, where the length of the list, integer divide by 2, and we're going to go all the way to the end of the list. So we'll leave what's on the right of the colon blank. That means go to the end of the list. So now we have 2 lists Right? We've split our sorted list, or it's a list of unsorted numbers. We've split it into two sections. Now what we have to do is we have to call our sorting algorithm on each of these two lists. So A, the way we have the sorting algorithm set up is it returns the sorted list and then some work. So we're going to say A and then work. Those are the two things we get back. We'll set those equal to the result of my sort. Remember, this my sort is a merge sort. And we're going to pass in A and then work. And here it's the same thing except B. So we're calling B and work. So basically, so far, this is recursive, and it's just going to keep dividing the list into halves, right? But at some point, our list is going to be the empty list, and 0 integer divided by 2 is 0, and it's just going to keep looping over and over. All right. So this, if we executed it right now, would be infinite recursion, but there's a recursion limit in Python, so we would recurse too far. We can go ahead and do that and see that we'll get an error. If I run merge and then I can pass in some numbers, 14, 13, 27, 7, 10, 35, 19, 42, 44. All right. Maximum recursion depth exceeded while calling Python object. Okay, so that's because this is just infinitely recursive. All right, what we have to do here is we have to have an edge case, an ending case. So when you deal with recursion, you always need an end case. So if the length of our list that we got unsorted is less than or equal to 1, right? Because if it's an empty list, we'll just return the empty list. If there's one item in the list, we'll just return that. Both of those two lists are sorted. So at the end of the mySort function, you should always return something that is a sorted list. Okay? So in our end case, the two end cases that are sorted lists is the empty list or a list with one item in it. So we can return unsorted. Actually, we'll make our duplicate first so we don't accidentally modify our list. Okay, so sorted is just a duplicate of unsorted, and now we can modify this one if we want. And so if the length of that list is less than or equal to 1, so if it's 1 or 0, just return the list. And that is technically a sorted list. All right. So that is our ending case. Otherwise, if we're not on one of those ending cases, then we divide the list into two separate halves and we sort those two separate halves. All right? Here we sorted A and B. We found A, it's the first half of the list sorted. We found B, it's the second half of the list sorted. Then we sort A, and we get A back and some work. And we sort B, and we get B back and some work. Then what we have to do is merge these two lists together using our helper function, merge. Right? And we've already tested merge out. We know that works. Okay, so all we do here is we say sorted equals merge, and we're going to merge two lists. We're going to merge A and B. Right? Merge takes two lists, A and B, and both of these lists should be sorted, right? Because we already sorted them here. Right? The reason this works is because there is an end case where eventually these lists will be sorted, and then we'll merge those. Okay, so let's see what we have so far. Not enough values to unpack. Okay, that has to do with this. So I have to return sorted and work. Merge returns merged list. That's good. Let's see, line 48. Oh, here, when I return sorted, I didn't return the work. There we go. So my sort always returns the sorted list and the amount of work it's taken. So here, sorted list and the amount of work. All right, so let's run that again. And we see that the sort succeeded. Okay. It's kind of a lot. We see that we had to have our helper function merge, right? And then merge sort, once we had our helper function, to merge two sorted lists, it was pretty easy, actually. It was just a recursive function. We duplicate our list. We have our edge case, our ending case of the recursive function. So if the length of the list is less than 1, less than or equal to 1, we just return it and return the work. Then we split the list. Otherwise, we split the list into two pieces, first half and a second half, and then we sort those two halves with the merge sort. And then these two lists are sorted, and then we simply merge them together. Okay, so we see that this succeeded. We compared that against the Python sort. So this is really good, but we haven't added the work. So let's see. Let's say we're going to add 1 unit of work anytime there's a comparison. So we're going to say work plus equals 1 here. I'm going to say that's for comparison. And then anytime we, let's see, do we want to do it when we split the list in two? I think so. I think we'll do it when we split the, anytime you split a list or compare items. All right, so we have, let's see, here's the sort. So here we're splitting the list. So work plus equals 1. And this is for list split. All right. And then in merge, we also have a lot of comparisons in merge. So we're going to have to, anytime we compare. So before this, in this while loop, each time we do this, this while loop, we're going to have to add 2 to work because there's 2 comparisons. We're comparing these 2 items. All right, so we'll say work plus equals 1. Comparisons. All right, and then we have another comparison down here. This should actually be 2 because there's 2 comparisons in the while. Then we have work plus equals 1 for this comparison. Right? Then we have another comparison down here. We should actually add 1 above the while loop too. The first time through the while loop, there's a comparison, right? And then there's a comparison at the very end that will eventually evaluate to false. So this is that one. All right. We can either have this one or not. It's not a big deal. We'll leave it out. So each time through the loop, there's the comparisons as the condition for the while loop, and then you check this. Then this is outside of the loop. We're going to have a work plus equals 1. This is an if comparison. Right? And so that should be all of the comparisons, but we have quite a few comparisons, right? 1, 2, so we're adding work 1, 2, 3, 4, 5, 6 times, right? Most of the other algorithms we don't do that, but we're going to compare these and see how efficient this is. So let's just run this with our new work variable work reference for assignment. Let's see, line 24. Oh yeah, I have to have work has to be passed in. Okay, so we have some work, and we always have to return the work. All right, kind of like we did with our sort function, we had to pass in the work to keep track of it. We had to pass in work as the argument, and so work is up here, and if it's not provided, it's 0. But we should always be providing it to merge. So merge now takes an additional argument, work, and it returns work as well. Okay, so merge some work, look for the return statements. It's just the one. Okay, so that should be good. Let's try it again. Okay, so 71 units of work. So this merge sort is working. So let's try 100 numbers. I created a little program here called Rando, and it just creates, you pass in an argument, and it creates a certain number of random numbers from, you know, a range from 1 to that number, and it randomizes that list and prints them out for you. Okay, so I'm going to call Rando 100, and this gives me 100 random values, pseudo-random values. Okay, so now I'm going to use this, and I'm going to call my merge.py, and I'm going to paste these numbers in here. And what we're going to do is we're going to compare the merge sort to bubble sort and insertion sort and selection sort. All right, so here is merge with these numbers. So 2,029 units of work. Now notice, again, we added work several places. Now we're going to compare that to, this isn't correct yet. We haven't analyzed this yet, so we're going to take a look at that in a minute. But that's what we're going to do here. We're going to compare this 2,029 units of work that was with merge. Now let's go through and do the other sorts that we've done so far. So we'll do bubble. Quite a bit more, 7,437. All right, so that was bubble. Then let's do insertion. Still quite a bit more than our 2,000, right? More than double, right? It's quite a bit. And then we'll try selection sort. And this was also 5,000. Okay? So all the other sorts were more than double the units of work. And granted, those units of work were a little bit arbitrary, but you know, we put them in there for a reason, because we were actually doing work there. So this should show you a little bit about the efficiency of merge sort. And we talked about it a little bit at the beginning, the concept of a tree structure. And we see anytime you divide and conquer, you're basically making use of some sort of binary tree structure. You have the main element is the root node, and then 2 subnodes, and then each one of those has 2 children, and each one of those has 2 children, right? So this is kind of the log n portion, right? As we divide this problem up into steps. And then when we merge, we do have to iterate through each and every item in the list, right? So that's basically another n. So what this winds up being is the time complexity of this winds up being n times log of n. Right, so if we run this again, merge sort, so the time complexity of this sort is big O n log of n. So this is the best sort we've had so far. And again, we saw it with our units of work too. That gives you a more realistic understanding of how efficient that is. Now we could make our work algorithms better, calculating the work. We kind of just added stuff in here, but we could add work for every single sort of calculation we do and keep track of things a little bit better. But that's quite a bit of effort. So this should be good enough to give you an idea of algorithm efficiency and why some algorithms are better than others. But in-log-in is a good algorithm. That's one that we can actually use in the real world. N-squared is not good. It takes a really, really long time to sort very, very large lists. In-log-in is much more doable. All right, so when you get into lists of size 1,000,000 or 1,000,000,000 or 1,000,000,000,000, it becomes a much bigger deal than when we're sorting lists of 100. Okay, so that is merge sort. And again, it was a recursive algorithm. So my sort here is our merge sort. And we had a helper function here called merge that joined two lists. Okay, so that should be enough for merge sort.